Hello everyone! In this lecture and the next lecture, we will study the Transport Layer Security Protocol, or TLS in short. So what is TLS? TLS is a cryptographic protocol that provides communication security over the internet. More specifically, what it does is that it provides confidentiality, integrity, and server authentication. The confidentiality and integrity here means that data is encrypted. And the server authentication here means that the protocol provides the ability to establish the identity of the server. As you will see, in practice, it relies on the public key infrastructure and public key certificates to provide server authentication. Now, what is super important, and I cannot overemphasize it, is that it is the most successful and widely used cryptographic protocol on the internet. Anyone who uses a web browser to browse the internet relies on TLS for security. There are some numbers saying that more than 70% of the internet traffic today is TLS encrypted data, so that's a lot. The TLS protocol has been smartly designed, and there are a lot of things to learn from its design and how it has evolved over the years. The protocol is relatively simple, and it is very useful to understand how it works because the same principles are also used in other communication security protocols that you will encounter. Usually, we talk about TLS in the context of securing web traffic, but actually, the TLS protocol is universal because any application protocol can be encapsulated in TLS. Here is a picture. So, usually, without TLS, we would have TCP packets whose payload contains some application protocol, some application data. For example, HTTP, FTP, SMTP, IMAP, POP, LDAP, whatever. Now, the TLS protocol adds the so-called TLS Record Layer, which consists of TLS record header. The record header simply tells us what type of data the TLS payload contains. It can contain 4 subprotocols, 4 different types of data. Handshake messages, change Cipher Spec message, and alert message, these 3 types of messages are used to establish, negotiate a secure TLS session. But most of the TLS packets will carry encrypted application protocol data here. So in the case of HTTPS, this payload here will contain the actual HTTP protocol requests and responses which are encrypted by TLS. So any TCP protocol can be encapsulated into TLS by simply adding this additional TLS layer. This TLS protocol layer should be invisible to an application developer. A TLS library should deal with all the TLS protocol peculiarities, allowing the application developer to use simple read and write calls to send and receive application data. Okay? Over the years, there have been quite a few TLS versions in use. In the beginning, it was called SSL, Secure Sockets Layer, but with later versions, it was renamed to TLS, Transport Layer Security. Here you can see the dates when the protocol specifications were standardized. Today, most of the traffic is protected using the TLS version 1.2 and 1.3 protocols. These other versions of the protocol have been deprecated due to security reasons. In this course, we will focus on TLS version 1.2 as this is the most widely supported TLS version on the internet. What is important to note is that the differences in all these protocol versions, except for version 1.3, are not too significant. Some fields have changed, some security bugs have been fixed, but in general the protocol stayed the same. Now, TLS version 1.3 is quite a revolution, because there even the order of handshake messages has changed. Therefore, to support version 1.3, not much of the existing codebase can be reused. Let's have a high-level overview of the TLS handshake, the most basic handshake between a client and server. Now, this is the most important slide of this lecture. If there is anything you will remember from this lecture, try to understand and remember this handshaking process. Okay? Okay. So the objective of the TLS handshake is to establish symmetric keys so that application data could be securely exchanged. And here is how it is done. So we have a client and server. Let's say the client is a browser, but the server is, for example, facebook.com. First, the client establishes a TCP connection to the server on port 443, which is used for HTTP or TLS. The first TLS message the client sends to the server is the ClientHello handshake message. In this message, the client informs the server about its cryptographic capabilities, tells what TLS protocols, what asymmetric and symmetric algorithms, and what hash functions the client supports. As a response, the server will send the ServerHello message, choosing a particular TLS version and crypto algorithms that should be used. After the ServerHello message, the server sends the certificate message, which contains the server's public key certificate. Now, this is the point where the client, based on the certificate, has to decide whether it wants to communicate with the server or not. So, what will the client do here? The client will check if the certificate is issued by a trusted CA, run revocation checks, see if the identity in the certificate corresponds to the server with which the client intends to communicate, and so on. After the certificate message, the server will send the dummy ServerHelloDone message, signaling that the server has finished sending handshake messages and now it's the client's turn to respond. If the client decides to communicate with the server, the client will now extract the public key from the server's certificate, generate a random symmetric key, encrypt this key using the public key from the server's certificate, and send this asymmetric ciphertext to the server in the ClientKeyExchange message. Since the server has the corresponding private key, the server can decrypt the random key, and that's it. Both the client and server now share the same symmetric secret key. An attacker who is sniffing the communication here does not have the server's private key. Therefore, the attacker cannot learn the symmetric key that has been sent by the client in this ClientKeyExchange message. So the key exchange is secure. Next, the client will send the change Cipher Spec message to signal that from now on, the client will encrypt data using the key sent in the ClientKeyExchange message. The client will also send the finished handshake message, which is the first message that is encrypted with the negotiated key and cipher suit. The server will do the same by returning its change Cipher Spec and finished messages. Now, by decrypting the finished message, both the client and server can verify the encryption with the negotiated keys works as expected. What is also important to note is that these finished messages will contain a hash of all previous handshake messages exchanged between the client and server. After decrypting the finished message, each party has to compare that this hash corresponds to the handshake messages that were exchanged by the parties. This check is important to detect and prevent downgrade attacks, because you see, integrity of these handshake messages is not provided. Therefore, the attacker could have modified some fields. By checking the hash in the finished message, both client and server can verify that they saw the same protocol transcript. For example, one possible downgrade attack could be to remove the strongest cipher suits from the client's ClientHello message, thereby forcing the server to choose only from the weak ones. This type of downgrade attack would then be detected at this phase. Now, if the verification of handshake messages is successful, then that is it. Encrypted and authenticated application data can now be exchanged in both directions. So, this is how a TLS session is established. This here is the most simplest RSA-based TLS key exchange mechanism. TLS also provides other key exchange mechanisms, for example, one based on Diffie-Hellman, but we will stick to this RSA-based key exchange because it is the most simple. Now, to summarize this process, the client verifies server's X509 certificate, the client extracts the server's public key from the certificate, the client encrypts a random symmetric key using the server's public key. Only the server can decrypt this symmetric key. Now, the client and server share the same symmetric key, and this symmetric key is used for the actual data encryption and authentication. Very good. So this is how the full TLS handshake looks. Now, to avoid this full handshaking process, every time we want to establish a new connection to the server, the TLS protocol allows the so-called abbreviated handshake to be established. which is also known as a TLS session resumption. The goal of the session resumption is to avoid the computationally expensive full handshaking process. Instead, we're using the cipher suits and keys negotiated previously. Here's how it works. So, to resume a previously established TLS session, the client would send the ClientHello message specifying in it the TLS session identifier which was given by the server in the server's ServerHello message in the previous full handshake. So here, in the ServerHello message, the server would include a unique session identifier, and here the client would include it in the ClientHello message, offering to resume that TLS session with the server. If the server remembers the TLS session with the session identifier, the server would return a ServerHello message with that session ID inside it, signaling to the client that an abbreviated handshake can be performed. And that's it. The client and server just exchange the finished messages to check that encryption works and can go ahead and exchange the application data. Now, if the server is not willing to resume the session, the ServerHello message will contain a new session identifier, and the client will understand that a full handshake has to be completed. So the client will revert back to the full handshake after these two handshake messages are exchanged. So that is how it works. Now, all resumed TLS connections share or reuse the same master secret that was negotiated in the initial full TLS handshake. However, the actual encryption keys for each TLS connection will be different because the encryption keys for each TLS connection are derived from the master secret based on the client and server hello messages. We will see key derivation on a later slide. But the point is that several TLS connections can belong to the same TLS session. Okay? Okay. Now, if a TLS connection fails, the TLS session may or may not become non-resumable. This depends on the reason why the connection failed. This is to prevent attacks where some garbage is resent to the server, and since the same or related key will be used, the attacker may learn something from a success or failure. So as soon as the server detects that something is cryptographically wrong, the server should refuse to resume sessions that use the same session ID. The session resumption feature is very important because this abbreviated handshake improves performance, saving one round trip across the network. So you see, one direction, another direction, and in the third direction, the client can already send the application data to the server. In the full TLS handshake, there was one extra round required. And it also saves at minimum one asymmetric crypto operation in case of the server authenticated TLS. So this has a significant performance benefit because asymmetric crypto operations are much more slower than symmetric crypto. And by the way, this use of asymmetric crypto in TLS can be abused to execute trivial application-level denial-of-service attacks against the server. An attacker can initiate a bunch of TLS handshakes, and the server would have to use its private key to decrypt the garbage ciphertext sent by the attacker. So there is some asymmetry involved. The server has to do much more work than a malicious client. In practice, this TLS session resumption feature is used by browsers a lot. For example, when we open a website that contains several images, the browser will not download these images one by one sequentially over the same connection. For instance, Firefox will establish at most 6 parallel connections to speed up the loading of the page. The initial connection will establish a full TLS handshake, but the following parallel connections will be established by resuming the initial TLS session. Very good. I hope that by now it is clear to you how the TLS protocol works on a high level. Since we will implement this TLS protocol in the homework, let's go over each TLS protocol message and see what fields it contains and what they are used for. Let's start with the TLS record layer. It contains 4 fields: type, version, length, and data. The first 3 fields comprise the TLS record header, which is here. The 4th field, data, is the TLS protocol payload, one of these here. So the type field specifies the type of the encapsulated data. As you see, the TLS record can carry one of the 4 TLS protocol messages: handshake, change cipher spec, alert, and application data. The type is encoded using a single byte. And here you can see the corresponding value in hex. Handshake messages are used to negotiate the TLS connection. As you saw, there are several types of handshake messages that can be contained here. The change Cipher Spec message is used to signal to the other side that the message that will follow will be encrypted using the negotiated parameters. The alert message is used to send warning and error messages, and the most important application data will contain the encrypted application data. For example, HTTP protocol requests and responses. The version field contains the protocol version encoded using 2 bytes. TLS version 1.2 uses these 2 byte values. The length field encodes the length of the data using 2 bytes. This means that the maximum size that one TLS record can carry is up to 65 kilobytes. And the data is one of these TLS protocol messages specified in the type field. Now, it is important to note that the data can contain several same type messages. For example, if you want to send several handshake messages, we don't have to send them over separate TLS records. They can be included in one TLS record concatenated together. This is how the TLS record header would look on the wire. There are 5 bytes, and we can look up what each byte denotes. The 16 hex means that the record contains a handshake message. The protocol uses TLS version 1.2. The payload of the TLS message is 61 hex bytes in length, and after the header comes the payload. Now, what is important to emphasize here is that the TLS record header is never encrypted. So, by sniffing TLS traffic, we can see what type of message the TLS record carries and what is the size of these messages. This metadata can give quite a lot of information about what is happening underneath. This is one very important aspect which is usually neglected. Software engineers usually think that, well, we need confidentiality, let's just throw in TLS and we are done. But what is neglected is that the size of the encrypted data can be used as a side channel to infer what the plaintext contains. Let me give you an example. Let's say we have some public website with a few pages that are served over TLS. Since each of these pages have different content as well as size, the attacker could deduce which page the user is browsing just by looking at the size of the encrypted response that is returned, right? So to prevent this type of privacy leak, all pages should be padded to the same size as the largest page in the website. This is the reason why, for example, Twitter pads avatar image files to fixed byte lengths, so that by sniffing the communication to Twitter, an attacker could not deduce which user's Twitter feed is being accessed. There was this nice proof of concept made by some researchers where they sniffed encrypted packets of someone browsing Google Maps over HTTPS, and based on the size of the encrypted payload, they were able to deduce, with some error margin, what regions the person was looking at in the map. So that's very impressive. This here is a good example where we see that the security definition of a cryptography protocol in practice may not meet our expectations of confidentiality. So be aware. And these type of side channels is also a problem in the analog world. For example, when you apply to some university in the United States, the university will send back the response enclosed in a sealed envelope over conventional mail. If you are rejected, the envelope will simply contain the message saying, "Sorry, you are not accepted." However, if you were accepted, the envelope would also include some additional information, and this would make the envelope bigger. So the fact of whether you are accepted or not can be learned without opening the envelope, just by looking at its size. So as you see, access to metadata, such as the length of the message, can introduce a significant privacy leakage in practice. Before we look at different TLS messages, let's take a quick look at how to dissect TLS with Wireshark. We can use Wireshark to sniff TLS traffic and inspect all bits and bytes exchanged. As you see here, we can traverse the TLS record layer and see the protocol fields and see which field corresponds to which byte here. For example, This is a 2-byte length field encoding value 49, and the 2 preceding bytes here are TLS version bytes. Of course, we cannot see the plain text of the encrypted data, but the TLS record header we can inspect in full. There is actually an option in Wireshark to specify the server's private key, and then Wireshark will be able to decrypt and show the payload as well. But it only works when the most simple RSA key exchange mechanism is used, the one we saw in the previous slides. Let's go now one by one through all the TLS protocol messages and see what they contain. Let's start with the alert message. The alert message is not a handshake message. It has a separate TLS protocol type. What it does is that it signals about TLS-related issues to the other party. It contains 2 fields, level and description. A level is encoded using 1 byte. It can be either a warning or fatal. Warning alerts are informative. Fatal alerts signal that something wrong happened and the connection has to be terminated. The description byte indicates the reason for the alert. Here you can see description codes in decimal and their description. For example, if the user closed the browser in the process of TLS handshaking, this user cancelled fatal alert would be sent to the server, and so on. Change Cipher Spec message is also a separate TLS subprotocol. It signals to the other party that from now on the negotiated cipher suit will be used to protect outgoing messages. And it contains a fixed byte with value 1. Nothing interesting here. Then comes application data. It contains most likely encrypted application data in a form as required by the application protocol. If this is HTTP over TLS, then this will be an HTTP request response, and so on. So it contains application data. The most complicated TLS protocol type is the handshake message, which contains protocol handshake parameters and is used to negotiate a TLS session. A handshake message contains the handshake message header specifying type of the handshake message, length of the message, and then follows the message itself, message body or payload. So the type is a single byte field that encodes the type of the handshake message. Here you can see the corresponding decimal values for the most popular handshake messages. The length of the handshake message is encoded using 3 bytes. And the body field contains the handshake message. Now, if you remember, the TLS record length was encoded using 2 bytes. This means that the handshake message can be bigger than what can fit in the TLS record. In this case, it will be split over several TLS records, and the recipient will have to reassemble these TLS records. So the handshake message body can be split over several TLS records. The maximum size that can be encoded in 3 bytes is 16 million. So the size of the handshake message is limited to 16 megabytes, which is fine. The biggest handshake message might be the certificate message, but 16 megabytes for the certificate message is more than enough. Very good. Now let's go over the handshake messages that we will have to use in our TLS handshake. So the ClientHello message was the first message where the client informed the server about its TLS protocol capabilities. It contains the highest TLS version number supported by the client encoded using 2 bytes. Now, this mechanism for announcing protocol version support is not perfect because it implies that the client supports all the versions up to this highest TLS version, which may not be the case. The client may decide to not support some lower version, which perhaps has a security flaw. So it would have been more flexible to instead provide a list of TLS versions the client is willing to use. Then comes the client randomness, 32 bytes. This randomness is cryptographically important because it will be later used in the derivation of TLS session keys. According to the standard, the first 4 bytes of this randomness should contain a Unix timestamp with the current time. This is a nice security feature because in case the client's random number generator is completely broken and let's say returns a fixed value, the client randomness will not contain a fixed value since the timestamp increases with each second. Yes, it will not be random, but at least it will be unique, resulting in a unique input being passed to the key derivation function. After the randomness comes the session identifier length encoded in 1 byte and the session identifier itself. This session ID will be here if the client tries to resume some previous TLS session. For new handshakes, the session ID field will be empty. Length will be 0 here. Then comes the cipher suits length encoded using 2 bytes, and then comes a list of cipher suits supported by the client, where each cipher suit is identified by a 2-byte identifier, and here is a list of some most popular cipher suits, and this is how the name of the cipher suit looks. Basically, the name can be split into 3 parts, where each part specifies what asymmetric crypto algorithm the server can use for authentication and key exchange, then what symmetric crypto algorithm is used to encrypt the data, and what hash algorithm is used for HMAC to MAC data. The TLS standard provides a list of standard cipher suits, but you can invent your own combination using a unique code for your cipher suit. After cipher suits comes the compression methods length encoded using 1 byte and the compression methods. There are 2 standard possibilities. 0, which means no compression, and 1, which denotes the gzip compression algorithm. So these are the mandatory fields of the ClientHello message. If there is anything left after these fields, then this data is interpreted as TLS extensions, which are optional. TLS provides some standard extensions which are quite often used. We will look at them in the next lecture. Now, after receiving this ClientHello message, the server responds with the ServerHello message, where the server specifies the TLS version selected that will be used for the connection. The server randomness, 32 bytes, where the first 4 bytes is the server's timestamp. Then comes the session identifier length and session identifier. This session identifier will contain the same session ID as in the ClientHello message in case the server is willing to resume that TLS session. Otherwise, it will contain a different session ID than in the ClientHello message, or it will be empty if the server does not support the session resumption feature. Then the message encodes the cipher suit selected by the server, which is encoded using the 2-byte cipher suit identifier. Then comes the compression method selected, and again, if anything is left after these mandatory fields, then it will be interpreted as a list of selected extensions. Okay? All right. In the certificate message, the server sends its certificate. Actually, a list of certificates. So it will contain the length of the certificate list encoded using 3 bytes, then the list of certificates where each certificate will have 3-byte certificate length prefix. And then comes the DUR-encoded certificate. The first certificate is in the list is the server certificate. Other certificates are optional. If present, then these should be intermediate CA certificates that are included to help the client to build the certificate path up to trusted root CA. The ServerHelloDone message is a dummy message with empty message body. This message indicates that there will be no more messages from the server in this protocol round. This message is needed because the TLS protocol defines a few other optional messages that the server can send to the client. Therefore, this kind of message is required to signal to the client that no more messages will come from the server, and now it is the client's turn to send something. The ClientKeyExchange message contains a 2-byte length prefixed encrypted 48-byte random key, which we call a premaster secret. This 48-byte premaster secret is encrypted using the public key from the server certificate. In the case of RSA, it is encrypted according to the PKCS1 version 1.5 standard, the same padding scheme you implemented in the RSA homework. The first 2 bytes in the premaster secret are actually not random, they contain the TLS version number. It must be checked by the server because this prevents some attacks where a ciphertext from a TLS session using one TLS version is replayed in another TLS session which uses another protocol. So this is a security measure. The next 46 bytes are truly random bytes. So this pre-master secret actually contains only 46 bytes of truly random data. But this is more than enough, as it provides 368 bits of entropy. The finished message is the first encrypted message. It serves to verify whether encryption works, and it contains a hash of the concatenation for all the previous handshake messages, excluding the TLS record error. Because otherwise, the hash value would depend on how many fragments were used for sending the handshake messages. The hash value must be verified by both parties to detect downgrade attacks, as we discussed before. Okay? Okay. Very good. We are done with the TLS protocol messages. Let's see now how the TLS encryption process looks. Here is a nice feature that nicely demonstrates the TLS encryption process. First, we have some data that we need to encrypt. It can be a TLS message payload or the actual application data we want to send. What we do is that we first split it into fragments, such that each fragment would not exceed the maximum size of the TLS record, which is around 16 kilobytes. Then we compress the plaintext fragment, if compression is used. The compression here is struck out because today it has been completely deprecated, as it turned out that plaintext compression leaks information about the plaintext. By knowing how well the plaintext compressed, we can learn how much redundant data was there. For example, if compression was applied, our idea of padding all pages to the same size would not work, because after compression, the length of the responses would still be different, and it would be possible to distinguish which web page was returned, right? And therefore, there have been more subtle attacks abusing this TLS compression feature. Therefore, it has been largely deprecated. Next, we calculate the message authentication code, MAC, for the plaintext, and append the MAC value to the plaintext. Then the plaintext with the appended MAC is encrypted. As you see here, the MAC is calculated over the plaintext and not the ciphertext. This is a bad design because before we can detect ciphertext modification, we first have to decrypt the potentially modified data. This has led to several side-channel and padding oracle attacks against TLS. There are workarounds to avoid these side-channel attacks, but the correct way would have been to MAC the ciphertext, as we did it in the AES homework. After the data is encrypted, we prepend the 5-byte TLS record error and send the encrypted data to the recipient. That's it. The recipient would decrypt it in the opposite order, finally reassembling the fragments to recover the original data that was encrypted. Very good. Now, how many symmetric keys are needed in this process? Can we use a single key for MAC and encryption? Probably we could do that, but the best practice is to use separate keys for different purposes. This also makes proving the security of the protocol easier. So what we need is MAC and encryption keys plus an IV for block ciphers. And we will use separate keys for each direction. Why? Because it is best practice in security protocol design, as it prevents reflection attacks, where the message received from a party is sent back to the same party. An alternative way to protect against such reflection attacks would be for each message to include some field specifying the direction in which it is sent. This is less secure because the parties have to remember to check that field, while if you use separate keys for each direction, this check is done implicitly. Very good. So we need quite a few keys. The question is, how do we derive these keys from the 48-byte pre-master secret that both parties have negotiated? Well, we will use the same idea that we use to derive encryption keys from short user-submitted passwords. We will use some kind of key derivation function similar to password-based key derivation function 2, if you remember it. For the purpose of key derivation, TLS defines its own key derivation function called PRF, pseudorandom function. It uses SHA-256 internally to produce infinitely long pseudorandom output. So it is basically a PRNG. First, from the 48-byte pre-master secret, a 48-byte master secret is derived. It is derived by passing to PRF the pre-master secret, a string master secret, the client randomness and server randomness, and here in the second argument specifying that we want 48 bytes to be derived. So this will be our master secret. Then from the master secret, a key block in the size needed is derived. This is done by passing to PRF the master secret, a string key expansion, the server and client randomness, and as a second parameter specifying how many bytes of key material we need. Then the key block is split into the keys needed. The first 20 bytes are used as a client MAC key to MAC data sent by the client. The next 20 bytes are used as a server MAC key, then the next 16 bytes as a client encryption key, the next 16 bytes as a server encryption key, and so on. Here you can see why resume TLS connections that rely on the same master secret will use unique keys. The keys will be unique because in this key expansion process, as an input to the PRF, the server and client randomness are also passed. So even though for the resume TLS sessions, the master secret value will be the same here, the server and client randomness here will be fresh and unique, and therefore unique encryption and MAC keys will be derived here. Okay. Finally, how is the MAC calculated? The MAC is calculated using HMAC. The hash algorithm used for HMAC calculation here is the hash algorithm from the negotiated Cipher suite. The key here is the client or server MAC key derived from the master secret. Now, as you see, there are several values that are included in the MAC calculation: seek, type, version, length, and data. Seek is an 8-byte sequence number that is maintained by the client and server separately. It starts from 0 and is incremented for every TLS record sent to the other party. The sequence number prevents replay and reordering attacks. If the attacker tries to do that, the verification will fail because wrong seek number will be used by the recipient to verify the MAC. The type, version, and length are the fields from the TLS record layer. This way, integrity of the TLS record header is also provided. This will prevent an attacker changing the record type and thereby tricking the peer into interpreting, for example, a handshake message as if it was application data and vice versa. And finally, the plaintext data that will be encrypted is MAC'd. So, in addition to data, a sequence number and TLS record is also MAC'd. After the MAC is calculated, it is appended to the data and encrypted. The data is then sent in a TLS record to the recipient. And this concludes the TLS encryption process. Now, the homework is to implement a TLS version 1.2 client that can retrieve a server certificate. So the client has to initiate a TLS handshake, get the server certificate, store it in a file, and close the connection without completing the full handshake. TLS getcert.py receives a server's URL and the certificate argument specifying where the server certificate in perm format should be written. The tool will establish a TCP connection to this host, in this example facebook.com, will send the ClientHello handshake message, and will get back from the server a handshake message which contains the ServerHello message. The tool should parse the ServerHello message, print the randomness, decoding the timestamp, print the session ID, and the cipher suite selected by the server. Then the server will send another handshake message, which contains the server certificate. The tool will print out the certificate length, encode the certificate to PEM, and write it in the file. The server will return the final handshake message in this round, which contains the ServerHelloDone message. After this, the tool will send an alert message and close the TCP connection. We could do it in a rude way by simply closing the TCP connection, but it is more polite to send the alert message stating that we don't trust the certificate sent by the server. So make sure that the alert message is sent, and you can see it in Wireshark as shown here. Fatal description certificate unknown. Perhaps you noticed that the TLS implementation of Facebook.com does not encode the current timestamp in the first 4 bytes of the server randomness. If we interpret random data as a date, this is what we get. Most TLS implementations today have deprecated inclusion of the timestamp in this field, and this is motivated by privacy reasons, because timestamp can be used as a fingerprint to fingerprint communication parties if their clock is skewed. Now, if your tool works as expected and the certificate was correctly extracted, the OpenSSL utility should be able to parse it. This is the subject name in the case of the Facebook.com certificate. Then there are 2 other test cases, Amazon.com and Live.com. The difference here, and make sure that your tool handles it, is that the TLS implementation of Live.com sends several handshake messages in one TLS record, while Amazon here encapsulated them in separate TLS handshake records. Your tool must be able to handle both cases, and it should be visible in the output whether these handshake messages were sent in a separate TLS record or in the same TLS handshake record. Okay? Alright. Some more instructions. Use Wireshark to see what bytes your code is actually sending over the network. Wireshark may point out why your message is malformed. Compare your parsed output with the decoded values shown by Wireshark on the previous slides. Use capture filter to filter out network traffic that you are not interested in. For example, this capture filter will sniff only those network packets that involve this host and this port. Note that one TLS record can contain several handshake messages. This is what you saw on the previous slide. Unix timestamp can be obtained using time function and casting it to int, because time also returns the milliseconds after the comma, but we are only interested in full seconds here. Unix timestamp can be printed out using datetime from timestamp function to convert timestamp to datetime object. Then we can print out what the datetime object contains in the format we like using the strftime method, specifying the format using the format codes year, month, date, hours, minutes, and seconds. So these are the instructions for this homework. In this homework, you have to implement only the beginning of the handshake, retrieving the server certificate. In the next homework, we will build up on this homework and you will implement the complete TLS handshake, sending some encrypted application data. In fact, it may be a good idea to complete the next homework while you are still in the TLS mode. This will also help you to better understand the topics that we will discuss in the next lecture. The topics covered in this lecture contain all the information needed to also implement the next homework task. Therefore, in the next couple of slides, I will provide the instructions for the next homework task. So the next homework task is to implement a TLS version 1.2 client that can obtain an HTTP GET response. TLS client.py that receives the URL as an argument. Here we can specify the port number if it is not the standard HTTPS port 443. So this is the part you already implemented in TLS getcert homework. Now you have to complete the handshake. First, the server's RSA public key has to be extracted from the server certificate, a random pre-master secret has to be encrypted and sent to the server in the ClientKeyExchange message. Then the change Cipher Spec message must be sent, and the finished message, which is encrypted and contains a hash of all the previous handshake messages. I will get back from the server the change Cipher Spec message and the finished message. We have to decrypt the finished message and verify the hash value. Then, in the application data, we have to send this hard-coded HTTP GET request, receive the encrypted application data from the server, decrypt it, and show the response. Finally, we close the TCP connection. So that is what your TLS client should do. Instructions. Your TLS client has to support only this one cipher suite, which uses RSA key exchange and the RC4 stream cipher for data encryption. The template contains a full implementation of set random function, derive master secret, derive keys, encrypt, and decrypt functions, and the client-server finished hash calculation code. Make sure that the correct inputs are provided to these functions. Don't look for an error there. If incorrect keys are derived, then the problem is that wrong inputs have been supplied to these functions. Grading is as follows. 2 points if the server accepted your client key exchange message. So it means you are able to correctly encrypt the pre-master secret. 2 points if the server accepts your finished message. That is, you correctly formatted it. And 2 points if your code can show the HTTP response, meaning that it can send the encrypted application request and read back the HTTP response. In the course repository, there is a TLS server binary executable which you can use for development. It is a self-contained TLS server implementation which provides very verbose debugging output. Running it, you can run it on some unprivileged port, let's say port 4433, so that you don't have to run it with root privileges. If you are using Wireshark to see the raw TLS packets that are sent over the wire, you have to configure Wireshark so that it can decode traffic to port 4433 as TLS traffic. Right-click on the packet, then decode as TCP destination port 4433, and select TLS protocol. By default, Wireshark will decode TLS traffic only if it is sent to port 443, so you have to adjust it if a non-standard port is used. Here is how the output from TLS server looks. As you see, it provides a lot of debugging info. Here you can see the encrypted and decrypted pre-master secret, the derived master secret, and here encryption and MAC keys. If something fails, you can compare where is the mismatch. So your TLS client has to be able to establish a successful TLS handshake with this TLS server. Note that this TLS server binary is guaranteed to work only on Ubuntu 22.04 and will probably not work on other Ubuntu and Linux versions unless you can figure out how to solve library dependency issues. You will notice that if you try to use your TLS client to establish connections to some random servers, for example, facebook.com or twitter.com, you will see that these servers will return a fatal alert after receiving your ClientHello message. Only Baidu.com and perhaps a few other servers will not reject your ClientHello message. The reason is because of the RC4 stream cipher that is used in the cipher suite that your client offers. This RC4 stream cipher is today considered broken. Researchers have found that the key stream generated by the RC4 PRNG has some small biases, and therefore it is possible to distinguish an RC4 key stream from truly random. This means that if we collect billions of ciphertexts that encrypt the same data, using some statistics, it is possible to learn the plain text it encrypts. And for this reason, the RC4 stream cipher has been deprecated in modern TLS server implementations. Well-configured servers today should not support it, but Baidu.com here does. We use RC4 in this task for simplicity, because implementing CBC with block ciphers would be more complicated. Just for you to know, there is this free TLS configuration testing service provided by Qualys SSL Labs. What it does is that it tries to establish a TLS handshake using all types of cipher suites and protocol versions. This way, it quite successfully enumerates a server's configuration, what TLS features the server supports, and what is the server's preference when selecting a cipher suite. It also assigns some security score from A to F. As you see here, the TLS implementation of Baidu.com is rated with B, not with A, because the RC4 stream cipher suite is supported and because outdated TLS versions are supported. TLS has very many options, and this is a nice tool to test if the TLS server implementation is configured using secure configuration parameters. Here is a list of the most common pitfalls when implementing this homework. If something does not work, you can refer to this list, which should hopefully help you to troubleshoot the problem. But okay, we are done for this lecture. Good luck with the homework.